So this example here is using all of the skills that you've got so far in this chapter, and also going and looking at bearings as well. So here the question asks, let I be a unit vector in the east direction and j be a unit vector in the north direction. So that makes sense because if you imagine your compass, I is in the east, so that's a unit vector, so length 1. So remember that the length of that I is 1, and north is defined by j, okay, which has a length of 1 as well. The first question says, show that the unit vector in the direction 60 degrees west is given as follows. So if we think about just drawing a set of axes here, and we'll mark in a different colour, we'll do 60 degrees west. Now west would be coming off of north here, so it would be kind of that much there, maybe a bit more, somewhere like that. So we've got 60 degrees here. And we've also got then 30 degrees here on that second angle. Now if we think about what is being said here, the question says show the unit vector in this direction has the following expression. That means that this vector here, and let's call this vector r, okay, the magnitude of r is 1. So this effectively is a triangle. I'll just do it in dark blue. We've effectively got a triangle here, and I'm just going to draw the triangle here using that bit of axis, where we've got 30 degrees, we've got a hypotenuse of 1, and this is our standard triangle. So this would be a half, and this would be root 3 over 2. So that's what this little triangle down here is. So then if we look at this, we can see that in the x direction we're going that way, negative root 3 on 2, which equals negative root 3 on 2i. And in the y direction, we're going up a half, and that would be a half j. So that means that to our point here, or this vector r, we can show, therefore, because of the standard triangle, okay, and we should say there, hence, as this is a standard triangle, we can see, and you can see there from the diagram, that r is equal to negative root 3 over 2i plus a half j as required by the question. Okay, so it's just a standard triangle that's been hidden, that little triangle there. So the key there was really identifying that that's the little triangle to use. You could use this one too, to the same effect. Part B is asking us if the car drives 3 kilometres in a direction 60 degrees west, so it's in the same direction that we previously travelled. And remember that this r here, in terms of notation, some of you might have thought about, we can express with the little hat on top because it's a unit vector. Oops. Can't get rid of that. There we go. So we're looking now at driving 3 kilometres in this direction. So 3 kilometres is 3 times this vector here. So let's call for B, we're going to say our position vector is 3 times as big as this vector here, because this is just going in 1 in that direction. It's going in the direction we want, but its length is only 1. So our position vector would be 3 root 3, negative 3 root 3 on 2i, plus 3 over 2j. That would be our position vector, travelling 3 kilometres in the same direction. So it's just that 3 times as big. Last part, we've now got an additional thing that's happening with the car, which is that the car then drives 6.5 kilometres due north. So at this point, it's really going to be useful to draw a proper diagram of what's going on. So I've just got the same thing on the next page. So far, our car has started at the origin. Oops, do it in red. And then travelled in the 60 degrees west direction. So we'll say about there. And it travelled 3 times the little hat vector r. So it travelled 3r. And remember that 3r we found before was given by this expression here. So I'll copy this one as well. So that was our first vector when we travelled off in that direction. Okay, 60 degrees. Now the next part of the question, and I'll just put the 60 degrees there, is saying that we're now travelling 6.5 kilometres due north. So we're going up that way. And we could think about this as being 6.5 j in that direction, because we're not adding any distance left or right, we're just adding distance up. Okay, so we're asked to find the position vector of the car. So I'm going to draw that in blue. So that would be, a vector that goes straight from the origin up to that point there. So if we think about constructing that now, we've really got this 3r vector, and let's call this vector r dash. R dash is made up of 3 lots of r plus this 6.5. 6.5 is 13 over 2 j. So that's the up part, and this is the part we already had from part B. We know that 3r hat is given by this expression, negative 3 root 3 on 2i plus 3 over 2j, and this is why I expressed 6.5 over 2, because it just makes it a bit easier to combine now. So we have negative 3 root 3 over 2i, and then here we've got plus 16 over 2, which would be 8j. So actually I have a nice whole number there. So that's this vector r dash here. This vector, it's our position vector of the car from the origin. So O to this point P, if you want to call it that. The next thing is it asks for the distance. So this is part 1. It then asks for the distance of the car from the origin, and we know that that would be just the modulus of r dash. So it's going to be the square root of squaring everything that we've got here. So it would be squaring negative 3 would be 9. Square of root 3 is 3 over 4. 8 eighths is 64. And if we put that into a calculator, what you will find if you do that is that you'll end up with 9 threes are 27 plus, this will be 256 if you times this by 4. And so I can take that 1/4 out the front. Square root of a quarter is a half, and actually everything else in there doesn't square out nicely. You end up with 283. So the distance of the car from the starting point would be a half square root of 283 kilometres. It doesn't say decimals, so if it doesn't say decimals, we'd have to do that in the exact form, so leaving it like that. Okay. The last part here is asking now for the bearing. What is the bearing of the car from the starting point? Now, if you think about the picture that we've drawn here, I'll just do in green, the bearing would be this bearing. What is that angle there? Effectively what we're asked for. So we could do it as a bearing west, or we could do it as a true bearing all the way around, but it's going to help us to find this here. So we know a few bits of information so far. We first of all know, we know this distance here, the blue distance. We also know this distance here across the top. So what I'm doing here is I'm forming a triangle. That distance and that distance there. We know this distance because it's the distance across the bottom here, which would be this. Okay, so this length here is actually 3 root 3 over 2, because that's the length, the I component going across here for 3r, and we know this length here, and I'll just do this on this side, is the magnitude that we just found. Okay, so we know that too. So we can do that as a half, 283. We also know this distance here, okay, because if we think about it, this distance is this part, which we know is 3 over 2. That's the j component of this vector here, the 3r vector, plus the 6.5. And we know from our vector here what r dash is, 6.5, which was 13 on 2. Remember that we found that to be 8. So we know that this length here is 8. So effectively, we could work with this triangle. 8, 3 root 3 over 2. It's a right angle triangle, and this hypotenuse is really ugly, so it's probably better not to work with that hypotenuse. So let's work with what we have. We could use tan here for theta, and I'm just going to get rid of this part up here where we found what r dash is. So we've now got, for our last part, part C, part 3, we've got that angle, theta. Tan of theta equals the opposite, which would be 3 root 3 over 2, over the adjacent. So that's opposite over the adjacent. And it's an ugly looking thing. It's a fraction on a fraction. It's effectively tan theta equals these two together, so it'll be 16 on the bottom, the 1 up the top. So 3 root 3 on 16. And so to find theta, we know that we can just do an inverse tan here of 3 root 3 over 16. Now we can use the calculator for that because that's non-standard. And I'm just getting rid of this part here. It's got a bit more room to move. Okay, so just using the calculator for inverse tan, it's 3 root 3 on 16. So inverse tan, 3 root 3 over 16. And I've made sure that my calculator is on degrees here as well by going into home. And I'll just get an approximate, 17.99. So this particular example, we've got theta equals, and I'll do it's an approximate 17.99 degrees. And we could pretty much just round that to 18 degrees if you wanted to. So the bearing, there's two ways to do the bearing. You could do it either as north 18 degrees west, okay, or you could do it as a true bearing, and that's going all the way around here. So it would be 360 degrees minus 18 degrees, which would be 342 degrees true bearing. Okay, so two ways to do your bearing. The true bearing is the more common way of seeing that bearing, and we got that result just by thinking about the triangle that we could form using the information that we already knew. So quite a difficult question, that one. It's a real application question for vectors, but a good one because it tests your knowledge of magnitudes, unit vectors, and also angles for vectors.